Hi everyone. My name is Erhan Kutanoğlu. I am the third name in the list. I'm the co-PI of the project. Actually, this project has finished already, and we have a published paper in computers and chemical engineering. And the student, it is not listed in there, but it is should be in here with Ray Park, who was the student in chemical engineering and mathematics department. He graduated already, and he's at Rice at this point as a graduate student. This is basically a project. We try to quantify the effect of uncertainty in circular economies. When we say economy, we are not looking at a whole economy of a country, but we are looking at a supply chain. And then we are trying to see how recycling or recovering material and used in conjunction with the fresh virgin material in a supply chain that produces things, and then we collect the waste, and then see how the uncertainty would be affected. Mainly because the circularity apparently, carries high uncertainty. Material quality is an issue, flow rate is an issue from stage to stage, and there's also legacy issues related to materials that have already accumulated in the environment. Like I said, we develop a stylized, quite simplistic model to quantify these things in a circular supply chain, basically one entity feeding another entity, and then we characterize the dynamics of the problem. We couldn't do a whole lot on the optimal management, but we tried to quantify the uncertainty for sure in this simple model. This is basically the state task network. I didn't know about this kind of tool before I got into chemical engineering friends, and then we start talking about this. But ultimately, the material process starts in the, well, it's a circular thing, but at least to explain the process, I want to start from the left bottom. And then you basically, combining some raw material, and converting into a finished product, you manufacture things, and then the product is being used, turned into waste. The waste is collected, and recovered material is reprocessed to make it into reprocessed material to be used in some cases in place of the virgin or fresh material, or maybe even in conjunction with the virgin material, potentially reducing the need for fresh, brand new material along the way. All right. It's a rather simple thing. It's whole thing is a mathematical model, really, and we use the mathematical model to simulate things, from stage to stage over time, and then see how things evolve. And since it's a 5-minute quick talk, there's a longer version in the poster, and even longer version in the paper, if you're interested. But this is basically focusing on the simulation part. As you can see, on the left chart, the inventory of the product that we have at different stages over time, changes quite a bit, and variability of it increases over time. Actually, the right chart shows a specific simulation run taken at different snapshots at different times, and you can see that the distribution of it itself goes wider and wider as time progresses. So this is based on Monte Carlo simulation. Of course, this kind of uncertainty and inventory variability amplification, if you will, has to be controlled if you want to take advantage of our control policies, optimal management of these policies, orders, production rates, those kinds of things should be updated. And that is the part that we are leaving for future work. How do we really manage the supply chain in an environment like this? That's pretty much it. Thank you.
Thank you. Next up, you're good. Next up is developing a network of ecological sensors for analysis of long-term acoustic and environmental data. Okay. Let's switch to the next one. Josh Busby or Nathan Jensen. Go clean fast, the political economy of green industrial policy. Hi, Josh.
May have to skip over a couple of these. All right, thanks for having me. Our project was Go Clean Fast, the political economy of green industrial policy. I'm Josh Busby from the LBJ School of Public Affairs. My colleague Nathan Jensen is in the government department, and we appreciated the support from the Energy Institute for this endeavor. The starting premise for the project was that intentional government policy would be required to hasten the clean energy transition. And as a result, we started thinking about this project before the Inflation Reduction Act was passed. And so we wanted to think about this nascent policy area of industrial policy, which had been out of favor for many years. So we decided to convene an online workshop in February 2023. And we invited participants to write short memos for us and record short videos to capture different dynamics associated with industrial policy. In part, with the passage of the Inflation Reduction Act, we wanted to discuss what were the political foundations of actually passing the act. And then another aspect, some of the writers tackled some of the downsides and risks associated with industrial policy, including the adjustment costs for fossil fuel dependent communities. Other folks drew on the experience of other countries who have already ample experience with industrial policy. We've always done industrial policy in this country, we just didn't call it as such, but other countries have nonetheless tried intentionally to do and support nascent clean energy industries, and so we wanted to learn from some of that experience. And so out of that, we generated a series of memos and videos, as I suggested, and then paid UT staff who are associated with video making to edit those into teaching tools. So we have both short and long versions of that, and we also have individual memos and videos associated with that. And I was going to show a 3-minute one that gives you a little bit of a flavor of the kind of work that came out of this. So let's see if this works. Okay, so I'm gonna, not sure if, hold on. I don't know how to make it work on this particular platform. Oh, I just clicked on it. Okay, I just wasn't sure if I embed it.
Oh my goodness. It worked before.
All right.
Can't be on full screen.
Oh, it can be. Okay. Oh, we're gonna need some sound here. Hold on one second. Oh, something happened here. Let me go back. I'm a Mac person, so this is, I'm gonna, is there a way to?
Bottom left corner, there's a speaker icon with an X next to it.
Yeah, I can, hold on. Mac people, it's not my forte.
The window, the taskbar.
Yeah, I got you. Yep, right this. Okay, that might be too much. Let's back out.
There's a recognition that typical energy transitions unfold over 50 to 100 years, and the urgency of the climate challenge means that we don't have that kind of time.
For the first time in history, something like the full financial weight of the federal government is now aligned behind the clean energy transition.
So I think that politicians felt that the public was quite concerned about this issue.
And the reality in these industries is that we rarely get these domestic industries, but we rather get sort of an integration of the domestic economy with much broader global supply chains.
According to the United States Energy Information Administration's 2020 Residential Energy Consumption Survey, more than 30% of U.S. households were challenged in meeting their energy needs.
That different countries around the world are at different stages of coal transition.
There are many cases now where we see incumbent industries who are working to advance clean energy. For example, we see legacy automakers building EVs. We see at least some utilities out there who are moving forward aggressively on 100% renewable or clean energy or net zero goals.
So civil society groups have gotten really good at opposing coal projects and targeting their finance, etc. A lot of this is focused around targeting existing plants in the US and Europe and proposed coal-fired power plants abroad. And through doing this, I think this movement has contributed to decreasing the social acceptance of coal.
Assets will be revalued as a result of both climate change and climate policy. And as a result of that, some assets will no longer be viable, some ways of life will be completely eliminated, and so people will fight like hell, basically, to preserve the value of their assets.
There are significant risks to decoupling from China in the clean energy sector in terms of jeopardizing our ability to meet global climate targets.
There's second some discrete arenas for cooperation where there's been some early positive signs. The global arrangement on sustainable steel and aluminum is one here, where the US and EU agreed to basically create a plurilateral docking mechanism in trade law parlance.
My best summary is there are individual videos from each contribution, also memos that are great and exciting, and in many cases ask interesting questions that maybe we can't answer yet, but gives us an incredible guidance on how to start to ask the question and to hopefully answer it.
Okay, well, so hopefully that gives you a little bit of a flavor of the kinds of memos and videos that were associated with this project. And there's more on the project website. So let me see if I can get back to that one. Oops, it's going to just keep on cycling. Let's see. Was it back in the presentations? Yeah. Not this one. Sorry. You may be able to find it for me. Sorry about that. Let me just say one more comment, and then I'll pass along. Okay. Did I click it on the wrong thing? Oh, do we have to go back to the IC? Yeah, there we go. Okay. So I invite you to take a look at the memos associated with the project on the project page. There are fuller ones associated with discrete topics from all the different scholars, many of whom you may know if you follow this issue closely. And we think we've sort of asked and identified a number of key research questions from which additional research can follow. So I appreciate the Energy Institute's support and hope you'll check out the material. Thank you.
Next, we're pivoting into industrial decarbonization. First of that category is breaking the hydrocarbon cascade in electric process heating, strategies for upgrading fuel gas streams.
Hello everyone, my name is Charan Nalapredi, and I'm going to talk about briefly our project on why there is a need to electrify industries and how we can convert flue gases from these industries or tail gases from these industries into green fuels, because most of these tail gases contain greenhouse gases, and if there is a way to convert these to green fuels, that would be great. So, talking about conventional chemical processes, to produce enough energy to create high temperatures and pressures, they use fossil fuels and they burn fossil fuels, and that would give out greenhouse gases. So that would increase the footprint of the process, which is not what we want. So what if we can electrify the process using sustainable energy, and that way we can lower the footprint. However, there is another problem with flue gases and tail gases from these industries. As you can see, for example, in Fischer-Tropsch's process, there is methane and CO2 in the composition of 2:1, and that's, again, a greenhouse gas, which we want to convert again. So what if we can use electrical energy to convert those gases as well into a green fuel like methanol? As you can see, methanol's demand is growing every day or every year. So that would be pretty compelling if we can convert these tail gas greenhouse gases into green fuels like methanol. Now, what else would be compelling? If we can do this at room temperature and atmospheric pressure. Conventional policies do it at very high temperatures and pressures like 30 bars and thousands of kelvins. We can do it at room temperature and atmospheric pressure. So how to do it? It's using something called plasma catalysis. So our design space for plasma catalysis includes catalyst activation, plasma excitations, and species transport. So when I say plasma excitations, what I mean is we use something called non-thermal plasmas, and these non-thermal plasmas introduce two different temperatures in the reactors, gas temperature and vibrational temperature. Although gas temperature is close to room temperature, vibrational temperature is almost 2 to 3 orders higher than gas temperature, and that drives the reaction forward, although the actual reaction temperature is room temperature. So as you can see on the plot on the left, when we add catalyst to this reaction, the red line shows the plasma-only reaction, and the blue line shows when we add copper to this reaction. We observed almost 3 times improvement in the methanol selectivity. So that's synergistic coupling between plasma and catalyst. But we add nickel instead of copper, that showed detrimental effect on the methanol selectivity. We observed 2 times lower methanol selectivity. The reason for that, we think, is because of high affinity of methanol towards the nickel catalyst, and it would almost try to get reduced or oxidized to CO2 or methane, back to methane. So the other parameters we're looking at is the union between catalyst activation and species transport. And we added a couple of trace amounts of oxygen or water vapor into the reactor to study the mechanism, which I'll talk about in the next slide briefly. The third parameter that we're looking at is the union between plasma excitations and species transport. This is just a play between time scales, meaning the reaction time scale and the species transport time scale, which is usually denoted by a non-dimensional number called Damkohler number. And as we lower the Damkohler number, we observed 7 times improvement in the methanol selectivity. Now, coming to mechanism, we're trying to vibrationally excite the species in the gas phase. We have methane and CO2. Because that's the most energy efficient way to excite the molecules. Now, to study the mechanism, we added trace amounts of O2 and water. When we add oxygen to this reaction, since oxygen has low adsorption energy on any transition metal catalyst, it would readily get adsorbed on any surface, so it wouldn't allow any other reactions to go through on the surface. Therefore, you don't really see much of methanol compared to the baseline, which is what we're showing on the plot on the left. So compared to baseline, we observed 35% lower methanol selectivity when you have oxygen in the reactor, because it's occupying all the catalyst sites, active sites. On the contrary, when we add a water vapor to the reaction, water vapor, it forms OH radical instead of O on the surface, and when you can form methyl radical in the gas phase, that would get adsorbed onto surface and form methanol readily. So that way we observed almost 40% increase in methanol selectivity compared to baseline. With that, I want to conclude my talk, and we want to thank Energy Institute for financially supporting this project.
So next is modernizing brownfield electric power systems reliability and quality to support the electrification of industrial processes.
So is the presentation. Oh, okay.
I think you can use this if you want to.
Okay, thank you. Does the mic work? Okay. So, hello, everyone. Today, I'll be presenting our research work for modernizing brownfields electric power system reliability and quality to support the electrification of industrial processes. I'm joined by my colleagues, Moises Chong and Woo-Sung Kim, who also collaborated in this project. And we were guided under the leadership of Dr. Surya Santosa, our PI, and our co-PI, Dr. Brian Johnson, as well as our collaborator at Shell, Dr. Lei Jiang. There are a few challenges in the electrification of chemical plants. First, we have the power generation side and transmission and distribution. And secondly, we have the reliability and power quality at the point of utilization. Control equipment is very sensitive to voltage disturbances. A single small voltage sag with a small duration cycle can trip motor controllers offline, such as variable frequency drivers. It may then take up to 24 hours to restart the industrial processes. Therefore, our objective is to modernize the power quality performance of the plant by eliminating the voltage sags at the load terminals. Sources of sags include short circuits and motor starting. Therefore, we reduce the sag impacts by including impedance grounding, high-speed relays and circuit breakers to clear the fault as fast as possible, and also reconfigure the circuit to increase the reliability. We can harden the equipment to allow it to ride through the sag, and we can also rebuild and restore the sag to its normal state by using a dynamic voltage restorer. Our accomplished work to date includes modeling of large industrial motors to simulate the industrial processes, variable frequency drive and respective controllers to increase the efficiency of the motors, and voltage sag ride-through characteristics to simulate the variable frequency drive under fault, the sensitivity of the variable frequency drive. We also did some ground scheme testing to limit the fault current, thereby reducing the voltage sag. And also we have preliminary models of the dynamic voltage restorer, which is used to inject voltages whenever we have upstream voltage sags. I should mention that this model wasn't part of our research project, but is included as an addition. We can see on the top left the industrial substation we have modeled. There is a fault in the system. We show the low voltage ride-through block connected to a breaker. We show the VFD, or the variable frequency drive. This model provides speed control, soft starting, and increased efficiency. And finally, we show a Siemens induction motor rated at 30,000 horsepower. On the left here, we show the typical VFD voltage sag ride-through capability curve. Whenever there is a fault in the system, the control scheme of the LVRT block detects it and starts a ride-through check cycle. Whenever we are in the green segment, and if the fault is cleared earlier, then the VFD is able to continue operation. However, if we reach the red zone of the capability curve, then a tripping signal is sent to the breaker, it opens, and the VFD is no longer in operation. We show two simulations. In the first, we show a fault of 2 cycles. This fault is in the green segment. The voltage drops down to around 55%. The power goes down as well. The fault is cleared on time in the green segment. Voltages return to normal, and the power goes back to 21 megawatts. In the second simulation, we show a fault of around 4 cycles. This barely touches the red zone of the capability curve. The breaker opens, and the VFD no longer operates. To avoid situations like this, we modeled a dynamic voltage restorer. This device is connected in series with the grid and the protected load. We protect loads such as power converters like VFDs, and the inside of the block is shown at the figure below. We treat each phase separately, connected to a series injection transformer, an inverter, and finally to an energy storage device such as a battery. On the right, we show the operation of the DVR. We see the source voltage in the top graph. Under normal operation in the left side, the DVR doesn't operate. Whenever a fault is introduced in the system, the DVR injects the missing voltages for each phase separately. Then we see the restored load voltages on the bottom graph. It's as if there is no fault in the system, and the VFD is able to operate or ride through the SAC. Future work for the DVR includes determining the number, the sizing, and the optimal placement of the DVR. Thank you for your attention. This concludes my presentation.
Thank you. Now we go to water use and conservation as a category. The presentation will be the effects of surfactants, salt concentration, and suspended solids on selective oil permeation.
Hi everyone, my name is Julie McGuire and I'm a first-year master's student working with Dr. Lynn Katz and Dr. Frank Seibert on this project to understand the effect of surfactants, salt concentration, and suspended solids on selective oil permeation, specifically with the goal of applying this technology to produced water treatment. As depicted on the top left image on the slide here, produced water is a major byproduct of the oil and gas industry, and it is essentially any water that comes up to the ground surface during the oil drilling process. Produced water can be highly contaminated, containing dispersed and emulsified oils, high concentrations of dissolved solids, suspended solids, and surfactants, along with many other constituents depending on the subsurface geology and chemistry of the specific reservoir. Currently, due to this complex and highly variable composition, produced water is very difficult to treat, resulting in the majority of produced water simply being disposed of, usually in the form of injection into deep underground wells. As water scarcity increases and the threat of water scarcity increases, the push and drive for the reuse of produced water is increasing as well. But again, due to the complex composition of the water, it is often quite costly to treat. This project is looking to see if membrane technologies, and specifically selective oil permeation, can play that key role in achieving the reuse of produced water and contribute to the circular water economy. A visual representation of selective oil permeation is shown here in the center top image. Selective oil permeation passes the oil of produced water through the membrane while rejecting the water, which is an atypical approach to membrane filtration. By passing the oil through the membrane, we see less viscous fouling of the membrane and actually increased oil recoveries over time due to the oil wetting of the membrane surface. Our process has been tested with multiple different synthetic water compositions, as well as on real produced water samples from the Eagle Ford Basin in South Texas, as can be seen on the right-hand side of the screen. The bottom right image compares the untreated raw produced water influent to our system to the Liquicell selective oil permeation membrane treated effluent. And you can see visually comparing the effluent to distilled water, we're seeing really effective results in removing this oil. So now let's take a look at how we've set up this process experimentally. The process begins by injecting an oil of known mass into a recirculating oil stream where it is emulsified into the water before being sent to our first membrane, membrane A. The effluent from membrane A is then sent to the larger of our two membranes, membrane B, where any residual oil is removed. The permeates from both membranes are sent to weigh scales and measured in order to obtain an oil mass balance for the process. Weigh scale outputs, pressure transmitters, and aqueous flow rates are all monitored, and the data is captured and stored using a data historian. We obtain the oil recovery efficiency data from membrane A under different process conditions and water compositions. So you can see the process flow chart on the left here, as well as some pictures of the actual setup at our high bay at the Pickle Research Center here as well. Our testing has shown effective oil permeation results. Here I've selected results from just 2 experiments we've run, but we've also tested the system under many other conditions as well. The graph on the left here shows the oil recovery performance for our raw produced water sample from the Eagle Ford Basin as compared to tap water with emulsified oil that contains no solids. Here we're seeing that there's very little difference in the performance of the real produced water to tap water, showing that the hydrophobic clay solid particles that are in the produced water have little effect on the oil recovery results of our membrane. It's also important to note that we're seeing effective oil recoveries at relatively low transmembrane pressures, and we're actually seeing the highest oil recovery rates at our lowest transmembrane pressures. On the right, we're seeing a graph of one of our longer-term operations here the membrane was allowed to run for 18 days straight, and we're seeing consistent recoveries throughout the process. And we observed no macroscopic evidence of viscous fouling of the membrane itself. We have other experiments where we ran the membrane for over 127 days consecutively, and we actually began to see improved oil recoveries the longer that the membrane operated. So that's all for my presentation today. Thank you for your time and attention.